And thank you for joining us for our weekly graduate seminar. Today, we have Dr. Steve Rogers, who is also a professional geologist with us. He is a senior principal geoscientist geomechanics with a degree in geology and Ph.D. in rock mechanics, with over 30 years experience in the field of fractal rock characterization with a focus on the creation of digital representations of rock fabric and structures in the form of DFN models based upon rich multidisciplinary data sets. Steve has applied these modeling techniques to a variety of mining applications, including caving and a large slope analysis, as well as fractured hydrocarbon reservoirs, both conventional and unconventional. Steve worked initially for the British Geological Survey for 10 years on the UK's radioactive waste disposal program before moving to Golden, now WSP, where he has been since 2000 in both the UK and Vancouver since 2005. He has delivered training courses on DFN applications to mining and oil and gas clients around the world and is an adjunct professor at the Norman B. Sewell Institute of Mining Engineering, University of British Columbia, where he lectures on the graduate level caving course. The abstract for the upcoming presentation is as follows. Discrete Fracture Network, DFN, models attempt to describe fractured rock masses using discrete modeling objects to represent critical structures, rather than as continuum descriptions. This has both modeling advantages and disadvantages. However, as a stochastic modeling approach, DFN methods do allow us to tackle some of the inherent structural uncertainties present in any analysis of a fractured rock mass and allow us to think about the probability of occurrence rather than just the probability of failure. Steve will discuss the basics of DFN modeling, some of the pitfalls, and focus on their applications in two main areas: the assessment of the inter-ramp stability in large open pits, and their use in the characterizing large copper gold porphyry deposits that are being caved. And with that, I'll hand it over to you, Steve, and feel free to share yours.
Sure. Right. There we go. Let me know if we're there.
All good.
All good. Excellent. So anyway, good afternoon, everyone. So thanks for that introduction. As with all things, I suspect the title, the abstract, and the presentation might have diverged somewhat in space, and so I do apologize. I'm just going to try and talk about some things. I hope there is some vague coherence to it, and I hope it's of use to you. The instruction was talk about anything that might be of interest to graduate geotechnical engineers. So here we go. Just by way of a bit of background, so I work at WSP, which was, lots of people knew Golder Associates. We got acquired about 3 or 4 years ago. So I sit within the WSP mining business, actually within the mine engineering and stability business. So kind of we do mining stuff, but that's just by way of introduction. So what I'm going to talk about today really is just getting you to think a little bit about how we think about a rock mass, and how there's maybe some different ways you maybe not so thought about, or maybe you have thought about how we can represent those, and then it makes it a little bit awkward because it then becomes a little bit disjointed. But I thought, well, I'll just talk about a couple of areas where I work in, which I think are interesting, which it just means it doesn't flow really as a presentation, but anyway, it's just a couple of things, and then just summarize. So anyway, that's what we're gonna talk about. So I don't even know if people talk about these anymore because I never hear them so much, but there's a whole thing about chilly, continuous, homogeneous, isotropic, linear elastic materials, or DIAN, discontinuous, inhomogeneous, anisotropic, and non-elastic. And so some different ways that we represent the rock mass. And I'm sure lots of you are sitting there in your offices running flat 3D models, perhaps, of representing a rock mass as a continuum. And in fairness, under lots of circumstances, it works fine. It always, as with all modeling approaches, they have advantages and disadvantages. I myself spent a lot of time working with David Eilman, our professor at UBC, working with, he did Elvin models, which are finite discrete element models. So actually trying to embed discrete fracture network models into those and representing. And again, there's some advantages and disadvantages with those. And anyway, what I'm looking at today is the fact that, you know, in a lot of the work that I do, not necessarily in terms of numerical simulation, but in terms of representation and what we can do with those, a continuum doesn't really work very well. We could use an approximate fabric. Lots of software has a way of putting some kind of simple DFN into a model. But really, I want us to think about, well, we put all this effort into characterization. Why can't we actually turn that characterization into realistic descriptions of the fracture network that's present within our whatever it is we're working on, and then try and use that for some different applications. And if we're going to do that, it means we've got to think about all these structures having some different properties and you know, different geometries, different sizes, different mechanical properties, different hydraulic properties. And that's really, you know, and some of the advantages that we might have by going down that route. Now, obviously, most of your work will be mechanical, but one of the problems with understanding the difference in properties of structures mechanically is you don't often know until it's too late. You know, we can do some shear tests and get some, you know, some joint strength properties, but the easiest way to understand how fractures have different properties is actually to think of them hydraulically, because hydraulically we can, you know, we can pump fluid through a fracture network all day and we'll actually understand something about how conductivity or apertures, you know, might change in a way that is much harder to do mechanically. So that's just, so I started out, a lot of my work was actually in fractured reservoir modeling. And, you know, some of the things we see when we interact with a fractured reservoir, or even just drilling drain holes in a mine, is we see lots of holes actually produce nothing. And some holes produce a lot. We see two wells that are drilled really close together don't communicate, but you know, a couple of wells drilled a long way apart might connect almost instantaneously. So we start to get a picture in our mind that it's the way that hydraulically a fractured reservoir works is poorly described by a continuum, just because there's some flow paths that have lengths and higher connectivities that mean that continuum description doesn't work very well. So just these pictures in the middle, if we just think about a network of fractures, so we've got, you know, would be like what your image log might see. So there's like lots of fractures, and we drill a well and we might count lots of fractures that intersect the well. But we have to throw away all of the fractures that didn't have, say, very much permeability or hydraulic conductivity. We'd have a much sparser network. And then we'd start to realize, well, that's kind of a little bit more how we see the networks behave when we actually look. So that on the right-hand side, that red histogram is just like saying, well, that's a sort of kind of what your FMI log might show in terms of fracture count down a hole. But when we actually look at inflows into the well, they come in very, very discrete steps. And often you might actually have just a few inflows over quite a long period. And it led this in a moment of vanity to coin what I call Steve's law of fracture flow, which is most fractures do very little, some do a bit, a few do a lot. And you could think of that actually as a literal description of a log normal distribution of permeability, which is what most people suggest is the distribution that we're looking at. So we know that permeability is distributed with some broad distribution. So we know size is distributed like that. So why shouldn't mechanical properties as well, and all sorts of other things? So now to help you to illustrate some of these issues, a number of years, gosh, a long time, more than 15 years ago, I made a little flow simulation of Vancouver just to illustrate exactly this point. So here's a picture on the left of Vancouver, and this this well here is at the intersection of Burrard and Robson, if you know where that is. And I'm sitting about here, actually. I think this is Robson Square. So I'm sitting just somewhere in between those two red stripes. And what I've done in this model, I've assigned different permeabilities to the 3 levels of kind of road network that I've got a GIS file for. So the blue are called streets. I've given them 1,000 millidarcies. Now, another thing I haven't really get into, but it doesn't really matter what these numbers are, because in fracture space, really, we talk about transmissivity as permeability times aperture. So fracture permeability doesn't actually mean anything. It's really the KH, it's the product of the K and the H. So these might have 1 millimeter of aperture or even less. So that 1,000 millidarcies might actually just be 1 millidarcy meter, 10 millidarcy meters and 1,000 millidarcies, depending on what I've given to it. But it's just, the whole point is we've got a low, medium, high perm. We put a well in that right here in the Robson and Burrard. And I'm just gonna let that flow for about 100 hours. Okay, so and what we see is as pressure flows out. So here we are at 10 hours. Most of the pressure is really still in Burrard and Robson. That's actually, you'll see there at 30 hours, you actually see this is the Lionsgate Bridge for those people who know Vancouver. So so the pressure's got onto Georgia and it's gone all the way over to the Lionsgate Bridge. And it's also kicked down here to this is the Granville Street Bridge, and that's Granville Island again, if you know the. They're at 50 hours. You see, you can see the drawdown on the major road. I should say I've thought about using this as a tool for traffic planning. And there we are at 100 hours. There's just some really interesting things we see. So just because of this distribution of conductivity, we've got this area in the this area in the West End, hardly any drawdown at all. This is just, we're looking at its pressure drawdown. Over here, we've crossed over into Kitsilano. This is the Granville Street Bridge. It's raced over here into East Vancouver, up Main Street. So you can just understand when you look at that, you go, okay, so some mechanical properties are going to behave a little bit like that, because what we're going to have in our world, we're going to have some big structures, some intermediate scale structures, and we'll have some small structures, and the small structures will have a certain characteristics, and the big structures will have a bigger, maybe so we'll have big, large, weak faults maybe that are going to dominate things. So it just encourages us to think, okay, really, perhaps we need to put those in, and we know that. But maybe we see those intermediate structures as well. Some of why the pressure is diffused all around here, around the sort of shopping area of Robson and Alberni and Georgia. So maybe we just need to think a little bit more about how we construct some models. So that's just by way, just to give you a little bit of a background of kind of why we want to think about that. So we think about in a mine, this picture on the right is a Chuquicamata, so one of the world's largest mines. It's more than 1 kilometer deep and probably about 5 kilometers long. So there's lots of structures, and there's actually too many structures to map. It's so big. So if we think about this sort of power law cartoon on the right, so we've got, the trace length of structures up to say, 10 kilometers, all the way down to a meter. This is the cumulative count. This red area of the curve up here, we know we can see them, we can map them, we can wireframe them, so we can include them in whatever model we want to do. But as we get smaller, it becomes increasingly hard. We know they're there, we can detect them. They might even be mapped, but increasingly they're not wireframed, so they can't be included. If we go even smaller, well, we know they're there because we can sort of see them, but they're not even necessarily detected because they're getting quite small now. They're definitely not, mapped, and they're certainly not wireframed. So the question is, how do we manage this? Where there's lots of things we've got to put into the model, but it's just really hard when we've got a big volume to deal with, and that's really where DFN models come in. This way of being able to stochastically add these things that we know they're there. But it's just really hard to wireframe, and we know they're important, certainly at a certain scale. And this interamp scale, where we're looking at things maybe in the sort of they're a bench to multi-bench scale in size. It's just really important. So just a little bit more for those people who don't know about DFM models is the idea is we're going to explicitly represent the structures that need to be put into a model in 3D space. And of course, it's important to understand when I say the structures that need to be modeled, you could build a DFM model of a 1 meter cube of rock, of a piece of core if you wanted to, or of a 1 kilometer deep pit. And clearly the scale, you've got to pick the scale you're going to work at. It's primarily a stochastic method. So we're going to generate features using some distributions of orientation, size, intensity, and we're going to include something about the sort of fracture architecture or spatial variation that we're going to include in that model. And there's many ways that we can make DFNs very, very structural, geologically realistic, or just very simple and practical. But the idea is we take the data that is acquired from geological, geotechnical, even hydrogeological investigations and turn those into distributions that we can use to generate these models. And because it's a stochastic process, it means, to some extent, we can have, it's a probabilistic assessment. So we can actually look at what is the likelihood of certain things happening. Should also stress the point above, we usually and typically include the wireframe structure. So we're almost like infilling the part of the model of the structures that we know that are there. We just haven't wireframed them, but we believe they're important enough. Where'd you get your data from? Well, it's just the routine investigation work that happens at any mine or probably, civil rock investigation. You have, mapped faults. We'll include those. There'll be increasingly, there's mapping or photogrammetry. So that actually gives us data, and that data tells us something about orientation. It helps us understand a little bit about size. It certainly helps us understand a little bit about the sort of that fracture architecture a little bit more. We actually looked at a little cartoon of a power law. I do like using power laws for these large models. This is this was some data, actually some work we did in Chuquicamata a long time ago, but actually showing that this is the different big faults mapping in the pit and even underground mapping actually can all be described on a constant power law trend. And by simulation, we can even demonstrate that that's realistic. So that's some of the data we use. So mapping, photogrammetry, boreholes give us orientation and intensity data here. And so really it's about, taking this data, developing a good conceptual fracture model, and then assembling it as needed. And we'll look in a moment at, how we do that. Now, interestingly, one of the things, lots of people do think DFM models are just what you might call a crack in the box. It's just we're going to throw fractures in of what I've called homogeneous here. But the reality is fracture networks often show, specific architecture, like they might be highly layered and ordered like here. They might be deformed and jointing might follow the beds, or faulting might rotate round over the scale of a pit or a large deposit, or we might see strong clustering of features around major faults. So the important thing is to try to do your best to try and capture that underlying kind of sort of structural concept. But, and I think this is a big but, when this is applied to engineering, it's really nice to have beautiful models, but sometimes we have to be a little bit more pragmatic. And the geotechnical engineer in charge of a pit slope, definitely wants something pragmatic and doesn't want, necessarily something that's structurally beautiful, because it's really important to ensure we have to trade, we've got to trade off validation. We know there's data rather than, geological inference and allowing structures to do things that we believe they do, but we don't necessarily see. So, like I said, at the bottom though, the message is a good model is one that honors the data, ideally has but has a sound structural model behind it. And I mean, just a couple of examples. So the one on the left actually is a sort of jointed, deformed rock mass. So there's kind of bedding joints within layers, but also other structures cutting through that actually make this is actually some slope sort of bench scale wedge analysis. You can see all these red wedges are unstable wedges, and then this model on the right is a much larger model, but it's cutting through a section just to show how we actually incorporated bedding faults into the model. They actually follow these lighter blue. It's within a quartzite, but there's a higher intensity of beds within the lighter blue limestone beds, so the intensity and the orientation is like following the limestone bed. So we can actually do proper geomodeling in a way of actually how we model these things. But again, that's something that we can validate and actually we can measure and show and then put into a model. So that's just some of the things. So anyway, what I'm just going to do is now just talk a little bit more around these two areas about some work that we've been doing using a DFM model and some limit equilibrium methods to look at sort of slope stability, and then also how we can use DFM models to look at characterizing copper porphyry deposits for cave mining. I don't know why I put that picture on the left, other than it's actually a DFM model taken into RS2, and I always really liked it. I just feel never forget that sometimes the stakeholders themselves need to be convinced, and realistic looking models often are far more convincing. Maybe they're not actually as valid mechanically. You're the clever people who get up and breathe constitutive models every night. Sorry, just a message came up. But maybe certain models are better than others, but never forget that actually just the power of visualization and a realistic model is often a lot easier to sell and convince people of. Right. Okay. So 25 past. Can you just remind me when would you like me to try and stop, and I'll make sure I give some time for questions.
So I think like 10 minutes for the question.
Okay. Yeah.
Good enough. So like 12.
Excellent. Yeah. Okay. Excellent. Okay. So look, let's just think about how we might look at, say, some kind of interramp slope analysis and design. So there's a few ways we can do it. We could use simple kinematic methods. We could use slices, limit equilibrium methods like slide. We could build complicated numerical models like FLAC3D or 3DEC, or we could use DFM models, and they all have pros and cons. Kinematics is really simple, but it doesn't really represent, there's no rock mass component within it. It's oversimplified, and it's really what I call possibilistic. It's not probabilistic. It's just what is possible. Limit equilibrium methods are great, but sometimes, particularly when you're looking at strongly structured rock masses, it doesn't really capture that very well, and it doesn't really estimate a probability of failure so well. Again, numerical methods, brilliant, really great, sophisticated, all sorts of mechanisms can be included, but they're incredibly computationally costly. So they just take long. So it's not, you can't necessarily have quite as much detail as you want, but also you might only be able to run, a couple of realizations. DFNs on their own, realistically very good, but then they don't capture a rock mass component. So again, listing from there, there's no real ideal method, which really led us to develop. Done a big project working at Bingham Canyon, realized there wasn't really an ideal design tool for looking at, a strongly structured rock mass that actually had, a unit that looked at having maybe these hybrid failure mechanisms of both rock mass and structure. There was nothing that was easy there that we could actually use. So we've developed this technique that we call DFN 3D POV, 3D probability of failure, really, after a team of marketing people working around the clock for a week came up with that terrible name, and that's what we live with now. But so let's just think about, here's a sort of an interamp stack. So it's 230 meters, about 14 benches high. I think they actually converted it from the US, so it would have been, I think it's 700 by 700 feet, but it's about 14 benches. Now, if we actually look at what we form kinematically, if we build a DFN model and then try and identify the blocks, you actually see there's kind of principally three kinds of blocks there. So what are called A, which are single bench scale stable blocks. Okay, we don't care about those, but we can identify them. There's what are called B there, which are simple wedges. They're one, maybe two benches high and unstable. And that's, again, that's relatively simple. And we can just, you could just say, well, if that's all we ever have to look at, then maybe simple kinematics is fine. But the biggest problem actually is the fact if we look at C, what really we would call non-daylighting wedges. They are multi-bench scale. So you can see their C is like about 6 benches, and this one up here is about 9 or 10. So they're large volumes of rock mass. It's potentially mobilized because or could be mobilized because it's a fully bounded block, but it's stable because it's actually sitting behind either it's sitting behind a buttress of rock or either at the toe or laterally, because obviously it has shape. So we need to, and you can't evaluate the stability of those using simple kinematics. It's not just kinematics, it's got this rock mass component. So really that's what we've set out to tackle. So we actually here's another example from a project, which is one of my favorite blocks we ever formed. So this block on the left is I call it the slipper. It's formed from a combination of the red deterministic major faults, but the green and blue structures are intermediate scale faults. So it's this combination of the two. So it's not just as simple as where are the faults. It's usually a combination of the two. But if we turn it sideways, we see it looks like it's a wedge that wants to come out, but actually it's not. It's a non-daylighting wedge. So it's actually sitting behind effectively this buttress of rock mass. And so if we want to actually evaluate the stability of that non-dilating wedge, we have to consider both the kinematics of the joints, but also the strength of the rock mass and, of course, the pore pressure as well. And so really that's where 3D POV came in. And my former colleague, Carl Lawrence, developed this custom slip surface algorithm. So it effectively searches the block and projects a slip surface out to the slope, and then calculates the factor of safety of that block, considering joint strength, rock mass strength, and pore pressure. So that's how we could do one of them. Of course, because it's a limit equilibrium solution, it's computationally very quick. So we just put in kind of these rock mass strength properties, calculates the factor of safety. But what we actually want to do, because it's so quick, we want to think about, well, why don't we run sensitivities at the same time? So we might have cohesionless joints, or lower GSI, or as well as a range of pore pressure conditions. So this graph here shows this particular wedge running it from dry up to effectively hydrostatic pore pressure conditions. So we use the RU as our input because it's just very simple and practical, and you can just see how the factor of safety as the pore pressure goes up is just falling. So that's one block. So we can do that for one block. So really the question then becomes, well, how do we do that for the whole slope? If we want to actually model the whole slope, what's our approach? So how we do it is, so we build our DFN model, and then we say it could be of an interramp stack, or it could even be a whole slope. We do both. And then in FracMan, we identify all of the blocks, of which there could be hundreds or even thousands for one realization. We then take those blocks into 3D POV, which then computes the factor of safety for each of those blocks, not only for its base case conditions, whatever pore pressure conditions, whatever strength conditions, but this suite of sensitivities. And then we throw them away and we go back to the beginning and we build another DFN model, identify the blocks, and then calculate the factor of safety of all the blocks. And the final sort of output, in a way, is just a massive table of blocks in certain domains with certain volumes with certain factors of safety that we can then interrogate, such that we can make, for instance, this could be a probability of failure sort of histogram, or it could be failure tons on a domain basis, or some kind of risk maps, heat maps that we produce that I'll show you in a little moment. So practically, this is actually some work from Bingham Canyon. So effectively, on the picture on the left is the sort of the FRACMAN output. So I said FRACMAN because FRACMAN actually does the simple kinematics actually within it. But so anything that's a non-daylighting wedge is assigned automatically a factor of safety of 100. It just means it can't compute it. So you actually see, so the FRACMAN is identifies actually, we've got this big failure here, which is actually a real failure, and all these other blocks. But then those blocks themselves are taken into 3D POV, which then computes the factor, a kind of real factor of safety, where it's actually considering rock mass. So you actually see this hotspot of sub 1 factor of safeties are, so this block is actually called the main hills failure. So that's one realization, of course, but we're going to run multiple realizations. So typically we run about 100 realizations, and then we can actually map this onto a grid. So what we're looking at on the left is it's called block failure percent. We actually, I think, call it now cell failure percent. And really, it's saying out of the 100 realizations in that cell, how many failing blocks did we have? Blocks with a factor of safety of less than 1. So, which effectively is a proxy for probability of failure, which would be, say, how many models failed out of the number of realizations. So you can see it's more proxy. So that's one thing. We actually see here these red polygons actually represent historic failures. So we actually see, apart from here, there's a bit of story which I won't get into there, but you see most of the historic failures we actually successfully identified using our because they had elevated cell failure percentages. But the other thing we can also think about is what we call the probability of occurrence, or probability of block occurrence, where we actually say, well, this isn't necessarily just thinking about failure, but it's just saying, well, where do blocks want to form? Because certain rock masses and configurations of slope, direction, and structure just have a predilection to make blocks, more favorably. And clearly, a block in itself is a potential sort of incipient failure. It might not fail, but just knowing where we've got a more blocky rock mass is useful. So that's some of the tools we've used to demonstrate that. And again, remember we ran all these sensitivities. So this would be the same. The images on the bottom are effectively the cell failure percent, but demonstrated or illustrated taking the failing blocks at dry pore pressure conditions, a little bit of pore pressure, and then hydrostatic. Interestingly, Bingham actually has some artesian pore pressures right at the bottom of the pit, which is sort of effectively down, down here. So actually, an RU of 0.4 isn't so crazy for certain bits of the pit. Anyway, but the whole point is you run this analysis once, but then you've got all of these sensitivities that you can interrogate. So it's just a very useful tool. And then, of course, we can actually look at calculating probability of failure. Just rather than doing it in a grid base, we can just say, well, let's just take the volume of all unstable blocks over the volume of all blocks within a domain, and we can actually start to see, which domains are the more unstable. Again, this is plotting, it's a number of domains, but with increasing pore pressure, because we have the data. So you start to see very quickly, what are the important controls. We could have similar graphs where we can say this would be the probability of failure, but for the low joint strength condition or the low rock mass strength condition. So again, very quickly identify what's important to a slope. You know, there's no point spending money on mitigations if you can demonstrate that maybe they don't actually make, or acquiring data if they don't actually, it's not a sensitivity. Okay, so that was a quick race through, you know, how we look at stability in slopes using this sort of DFN and limit equilibrium solution. But that's just for the last 10, 15 minutes, we'll look at caving application. So this is a model that myself and Davide Elmo produced years ago when we were working for Cadia East. Cadia East is a large gold copper mine in New South Wales owned by Newmont, formerly Newcrest. So for those who don't understand caving, the idea is that you develop a whole series of tunnels underneath the mining block, and then you develop these drawbells, and then you undercut above the drawbells, which causes the rock mass to collapse into that void, and then is drawn down through the drawbells. And obviously, as you draw it, you make more void space, and so it continues to collapse. And you can see how the cave evolves upwards. And these mines are in many ways the future of copper production as we're running out of large open pit deposits. Lots of the deposits themselves continue underground, and this is a mass mining method. The last year, the GBC cave in Grasberg, so in Indonesia, achieved a record of something like 150,000 tons in a day. It was a huge. Is that right? It's an insane amount of production. Insane amount of production. And that's the biggest, and no one will beat it. But we should never say no one will. But anyway, they're big mines, and it's very much the future. But one of the problems with them, just to give you an idea, is they're very capital intensive. You can see here, all of this infrastructure has to be developed before you start caving. So that's like, you know, it's hundreds or thousands of kilometers of drifts that have to be developed. And because they run for a long time now, like Cadia is more than a kilometer deep. So it's a super, you know, the modern, we've called that, now this is an old graph, you know, it's called super cave block heights of like, you know, 1,000 meters. So develop all this, and then you start hoping. And really, you know, that's one of the reasons we got involved, was so, well, there was an awful lot of very disappointing results from caving. And it turned out, to some extent, the fundamental rock mechanics was not right. So if we think about a conventional jointed rock mass, it's defined with open structures. We've got kind of removable or kinematically movable blocks. The failure mechanism is typically shearing and rotation of these sort of joint-bounded blocks. Not necessarily that much rock failure, but the rock mass itself has little tensile strength. Excuse me. And you know, there's lots of systems like Q and GSI and RMR and, you know, a million other different classifiers that are really all designed for this kind of system. But in porphyry deposits, where the picture on the top right is, one of the characteristics are they have very, very few open structures. They have some small faults, but really the primary kind of structure, discontinuity structure within them is a vein network of different vein minerals. So really we've got cohesive features that have got tensile strength, and they form in situ, you might call them incipient pseudo blocks. They're not yet blocks. They might be, but they're not currently. Shearing and rotation is inhibited because, you know, this is all glued together. It's not like the picture on the right. And so really the existing systems like Q and GSI and RMR are just not actually very good at characterizing the system and given. So effectively what happened was the rock masses were sort of mischaracterized. And so when the designs were implemented and caving started, they didn't really start. Famously, for instance, Grasberg spent something of the order of $1 billion to re-engineer DMRZ because it was just a completely massive cave, with almost nothing for it to break along. If we just look at just some pictures from cave, these are porphyries around the world: Indonesia, Chile, Australia. It's how actually remarkably similar there are, and this characteristic is they don't really have very many or any open joints, and it's just this sort of network of veins. So clearly we need to be thinking about the veins a little bit more. The reason being, if we actually look at if we go to the draw point and look at the blocks, we'll actually see that, the majority of the blocks are actually broken on vein faces. So we say, okay, also, although they have some strength, and maybe not all as strong, and my good colleague, Andres Brozovic, who worked at El Teniente and Grasberg for a number of years before joining us, he did his Ph.D. looking at vein mineralogy and found that really it was the softer minerals, weaker minerals like gypsum or chlorite and anhydrite, in his case, even chalcopyrite, that was the face of all these veins. So we have to think, okay, so how do we use this information? So, before a cave is developed, there's lots of drilling, and from the drilling we have core, and we can start to see all these different veins. Now, and we've done lots and lots and lots of point load testing on these veins. We've actually found that we can kind of break them up almost into two broad groups. As someone who does probabilistic things, I'm a little bit uncomfortable with this broad classification of weak and strong, but effectively we're saying the minerals that have whose median is below a IS50 strength of 1 megapascal, we're calling weak, and those that have whose median strength is above 1 megapascal is strong. But it kind of makes some sense, in the sense we see, clay and gouge and sericite and chlorite and certain carbonates, minerals as the weak ones, and then sulfide, chalcopyrite, quartz, pyrite as stronger ones. So what we do with that data is, so remember we've got logged vein intensities. Now this is just some DFN stuff. People might have seen my former colleague Bill Dershowitz developed this a long time ago, 30 odd years ago. So we use this term P32 is the holy grail of intensity metrics, which is the fracture area per unit volume. So that's the measurement along the top and the dimensions of the sample. So it's a 3-dimensional sample and it's a 2-dimensional measure. So it's the area per volume, P32. Fracture frequency is effectively what we call P10 here. Obviously, it's a 1-dimensional sample and it's a count. It's a 0-dimensional measurement. So what we want to be able to try to take the vein logged P10s of the critical veins, and only the critical veins, and turn that into a P32 that we can start to use that, because it turns out P32 is this wonderful intrinsic property. It's an isotropic measurement of fracture intensity, and it's really useful. Correlates with things like permeability, stiffness, block size. Just to show you, actually, here's a graph of, so we actually have by just some little simulations, if we build some DFN models with increasing P32, we see as with increasing P32, the actual median, or the P80 block volume diminishes. So anyway, so then what we can do is we can actually start looking at different P32s. What actually does the rock mass look like? What's the block volume? And these are just some simulated caustics, just saying, billions of dollars hang on which caustic represents the caving rock mass. I haven't really got time to dwell on that, but it's worth bearing in mind. And we send often our cheapest people to log core and that is the data from which billions of dollars are based. Again, we can even look at, okay, when we go underground, or before we can go underground, as I said, visualization is often the key to actually selling the idea. We can start to think about, which of these rock masses represent our cave, and it could be all of them, because it's not one size fits all. Now, this is I'll just really finish off with this. So we had to answer the question, okay, so how do we actually try to benchmark different caves against themselves? And so we developed this matrix, which we call the sort of veined rock mass matrix, where across the top, we have an increasing intensity of weak veins, and going downwards, we have increasing intensity of open structures. Like I said, so faults, typically faults, but there are occasionally some joints. And we say, so where might we be on that model? So here's just some examples of some different rock masses. Here's a sort of massive one with like nothing sitting there. We've actually got, here's our example that we saw from a more classic rock mass. So it's actually got low weak veins, but it's got relatively high open structures. And then we found, well, we can actually sort of designate areas on these graphs. And I should say they're kind of slightly specific. It's not entirely yet universal, but these black lines represented. So everywhere to the right of this black line has a median block volume of less than 0.1 meter cubed, and everywhere to the left of this black line has an average block volume greater than 1 meters cubed. So we've got these three areas. And when we started to find that, then we could say, well, broadly actually related into, so anywhere in zone 1 is going to have cavability and fragmentation challenges. Zone 2 is a sort of, we'll call it the Goldilocks zone of, things should cave and we'll have extraction level stability. And then zone 3, it'll readily cave. You'll have incredibly fine fragmentation, but you're going to have, significant extraction level instability. So that's, and then we found ways to actually drop on lots of cave projects we've worked on into this framework, and we found it shows very, very good agreement. So it's a really simple way to visualize where a caving project sits and what's the likelihood of what we expect. Of course, in terms of this P32, see, we can actually block model that P32. Since P32 equates to actually the block volume, we can actually make some predictions about the likely fragmentation of the block volume, where it'll sit. Where a particular part of the cave will sit in terms of that matrix. So I thought there was just by way of summary, look, I think DFN modeling provides an efficient way to model smaller intermediate scale structure that it's too numerous to do accurately. So we'll just do it stochastically, and it allows us to capture some of the uncertainty associated with the structural modeling because it's multiple realizations. Hopefully it's a way to be both sort of complex, but also pragmatic, and providing this better route from characterization to representation, ultimately to communication of some results. But I said seeing is believing, and the stochastic nature of the DFNs, just do allow a probabilistic assessment to be carried out in a way that's just not really very possible with more heavyweight numerical analyses. So I did say maybe no one ever talks about Chile and Diana, but I'd just like to suggest that we should add a third one today, which is, we'll just call it Steve, which is statistically true, engineering valid, and effective. Now, maybe it should have a question mark at the end of that. But anyway, thank you very much. Anyway, and there you go.
Thank
10
you
minutes
very
for questions.
much. Yeah, thank you very much. And I like this Steve abbreviation. Yeah, that was cool. So we have a couple of questions coming, which is nice. And please, if you haven't typed in your question, type in now. So Dr. Sebastian Lopez has a question, and that question is regarding fracture roughness, which may be related to scale. What is your
fracture
roughness? Yes.
Yeah.
What is your view on incorporating roughness into flow through fracture network?
Into flow, was that the question?
Yeah.
Roughly, yes. Well, of course. Well, actually, I mean, roughness is critical when it actually comes to flow, because really lots of people talk about fracture aperture, but the reality is there is flow aperture, storage aperture, transport aperture. I think I'm even missing one. So I'm sure there's a fourth one. And so all of those, roughness, however we want to define it, is a fundamentally important part of how we ultimately define aperture. So if we've got very, very kind of rough and jagged fractures, that will have maybe a very high storage aperture, but might have a very low flowing aperture. So, there's that whole parallel plate model. We should go and break the parallel plates, really, because they're just very unhelpful. More realistic descriptions of that actual fracture space is useful. But again, because like I said, I am a bit of an accidental modeler, but I'm a pragmatist. So we go, it is difficult because it's going to add a level of complexity when you do flow simulations. How do we exactly, if we can't constrain it or we can't actually put it in the right place in a model, it becomes hard. We might be able to globally reproduce things. But anyway, it's a great question.
And we have Dr. Bojang that says, great presentation, interesting to see the visualization of the fracture network in the cave simulation. What is the methodology to model the dynamic fracture in your model?
What do we mean by dynamic fracture? Like how a fracture responds to stress, or I'm not quite sure. I mean, maybe how we model in terms of so a lot of what I've seen in terms of what I've just shown today, there's no actual dynamic modeling of a fracture. So they're kind of static. So it's, say take the slope modeling, the fractures themselves were just modeled as a sort of almost, we're forming blocks and they've got some kinematic properties. So it's just, they potentially could slide, and the slip surface allowed an equivalent joint to represent rock mass strength. However, within FracMan and within other tools, obviously you could actually have more coupled responses. So actually giving those joints stiffness that will respond, so that the apertures and would actually change during loading. But nothing I've shown you today really, I think would call it a sort of dynamic response.
I see this. Yeah. Okay.
Yeah, it's me, Bo. Yeah, for some reason I cannot open my video because host stopped it. But my question is regarding to the one of the cartoon that you showed for the cave simulation, where we could clearly see the mobilization of the fractures. Maybe it's more like a visualization, or we could actually model the fracture propagation and also the mobilization of it.
Yeah. Oops.
It's cartoon. That's right.
There we go. So sorry, what am I looking for? So it's it is a realistic model in that, cave, the material has been drawn from the cave and the cave is collapsing.
Yeah, that's right. And you could see you have installed DFN already in the model, but when you are doing the caving, we could clearly see there are a lot of small fractures that has been developed inside of the cave, right?
Yes. Yeah, that's this software is Elvin, which is this finite discrete element model. So there's blocks, the blocks themselves can break. So it's not just, so we've got again, it's a hybrid failure mechanism. We've got, part of the failure is associated with the DFN, so the existing structures in the system. And then obviously the intact rock does break as well. But really we should think of this model as it's a rock mass model. Mm-hmm. I can't remember the element size might be of the order of, say, 10 meters, maybe even more, 20 meters. So that within that modeled block of, say, 20 meters, that might actually really kind of comprise half a dozen incipient blocks. So we might just be, even though we're breaking the rock, we're really breaking the rock mass. But anyway, but yes, but the whole point is it's demonstrating the hybrid mechanism of failure associated with faults, joints, and the rock mass itself.
Interesting. So what is so you mentioned it's Alvin, right?
Yes.
So what's the computational efficiency for this model?
Oh God, pretty slow. They're not fast models. These models probably took a week or two to run. Back in fairness, this was this was about 2009. So 15 years ago. The same code. There's a Canadian Geomechanica. Probably you've come across them. It's a very similar code, which is faster and more beautiful.
FDM, right?
But they're both FDEM. They used to call them FEMDEM, and then for some reason it became FDEM. But anyway, yeah. So they're slow models, but they're very, very good at illustrating, particularly in 2D. In 2D, you can have this sort of fracturing process. In 3D, they don't typically do 3D fracturing, but in 2D, it just works so well. And we've done it and I've seen Davide's published other things on, slopes, reproducing Brazilian tests. Here's caving, or just pillar failure in mind. So it's a brilliant way to take a more realistic description and then have actually model the actual fracturing process rather than an approximation.
Interesting. So in Alvin, do you need to install all these small fractures? That is actually
no. There's just it's just a mesh.
It's a mesh.
It's just a Voronoi mesh. It's not even right. It's just a triangle. It's just a triangular mesh, and the mesh breaks.
Okay, so that is probably you have that cohesive element in the mesh, right?
Yeah.
And actually, the mesh opens or it creates a fracture.
Yeah, so you can see, when it starts up, so all these the part that's flowing now, that's all broken material, but that's come because the mesh itself has actually broken down to its, so I don't think it will split. I don't think it will split below the smallest element, but it will break elements. So it's conceptually similar to the to UDEC and its Voronoi sort of mesh, although it's a little bit more efficient than that.
Okay. Well, thank you very much, Dr. Rogers. Very interesting talk.
You're welcome.
Thank you. And we have one more question in the chat and more questions from me. We have John saying that, hello, I would like to know how we can determine in advance whether a fracture is a dilating fracture or not. And what effect does the dilating joint have on the mode versus the non-dilating joint? And I believe.
Sorry, can you repeat the question? I didn't quite hear it.
He wants to know that how we can determine in advance that whether a fracture is a dilating one or not, and what is the effect of a dilating joint on the mode of the fracture, I believe, versus the non-dilating joint.
Okay. Like I said, well, to go back to a previous answer, so in the kind of the slope modeling I showed, that wouldn't, in that particular case, it's not particularly relevant. As I said, we're not dynamically modeling the response. If it was a full scale slope model, so a three deck model of a particular structural fabric that you were actually doing full stress analysis on, you don't necessarily know beforehand. I guess you can infer, but I don't know if you can know beforehand, which is necessarily going to be dilatant and which is not going to be dilatant. So I guess that's one of the reasons why you have to interrogate your model afterwards and see, you know, what kind of failure has actually happened. And so I'm not sure. Yeah, it's a kind of hard question to answer within the realms of what we talked about. But so I'll have to finish on a failure, unfortunately.
Yeah, okay, thank you very much. If you have a couple of more minutes, I have some questions.
Okay, sure. I'm just gonna turn that off. There you go. I'm gonna go back to my face. If that's...
Yeah. So actually, thank you very much. It was a very comprehensive presentation. I loved it so much. What do you think is like how the lab testing, like for example, UCS and Brazilian test, like can affect the results of the simulations? Because so there are point data, right? And you want to upscale them at like your like field scale. Like, how do you think that if we increase the number of the point data that we have, is that really gonna have a very huge effect in the upscale model?
I think it does actually. So there's been a lot of work in the caving space where they're increasingly going to continuous point load testing, like maybe every meter, and then, or certainly for large sections, and then they've used some various AI and machine learning techniques to be able to produce effectively high resolution PLT curves down, you know, on all holes, which then means you can then start to actually try and block model. That, you know, that's effectively it's the intact / mix because it might be on a vein.
Yeah.
Sort of strength properties through the cave. Now, I mean, one of my, you know, I didn't really stress the point too much, but one of my irritations is people talk about the monzonite domain rather than going the good monzonite, the average monzonite, and the bad monzonite, because we know these properties are varied, you know, and obviously, I think one of the problems is a lot of rock mechanics culture was set a long time ago. So in the early days of numerical modeling, you know, nobody wants to build a numerical model where you've got highly distributed stiffnesses because it takes the matrices take forever to solve.
Yeah.
And so that's probably one of the reasons why we own, okay, what's the stiffness of the monzonite and what's the stiffness of the cyanite, you know, whatever it is. Whereas now, you know, machines are a lot quicker and maybe we should actually revisit these things and say maybe we actually need a little bit more fidelity in how we characterize our models. You know, we have the data. Increasingly, people are seeing the value in it because in a cave, whether it's, you know, strong or weak, has fundamental implications for how the cave will behave. And therefore, it might need to be actually used within the actual planning. So we might want to be drawing the deposits because obviously how we draw it will affect how the cave will evolve. And so so it has you know major inputs if we have that resolution and we have more data, but it's are we actually using it yet? And in caving increasingly, but lots of other places not at all. So
yeah, good to know. And please correct me if I'm wrong, but what I understood is that 3D POF is like another separate software that you get like the outputs of the fragments and import them into 3D POF. Is that how it's works?
Currently, yeah. At the moment, what we effectively do is we export all the blocks and then suck them into 3D POF with a new pitch shell, and we're actually trying to import that into FratMan. We developed we developed that here in Canada. I mean, we work with FratMan, but we're not the FratMan kind of group. That's in the UK. So anyway, we're trying to see if we can actually get them to import it into FratMan, so it actually then become, you know, a seamless process, and it'll just get run and spit out all the results.
So what's the format of the data that the 3D POF gets? Like, is it like, does it read VTK files?
It actually 3D. Is that a ParaView file? What's a 3D?
Oh, okay, yeah.
Yeah, so we use ParaView, but I think we actually export the blocks as in a GoCAD format, a TSURF.
Yeah, okay.
They're very similar. It's just like, you know, it's just nodes and topology. It's very, you know, it's actually a pretty simple format. But so we export potentially 100,000 blocks but then 3D POV is just going to quickly go through and go, and literally it picks up a block and says, oh, this is in domain 1. These are the properties of domain 1. Here's all the sensitivities. Here's all the factor of safeties, and it just writes out a massive data table of all these blocks. So we just have this sort of big data table with that we just interrogate.
Oh, cool. And is the 3D POV an open source software, or like is it licensed? Like if someone like me wants to just like get access to all this stuff.
It's not licensed and it's not open source.
And then is there a possibility of a student?
There is a possibility. And who is Renato? I've spoken to Renato in your department.
Yeah.
We've chatted a couple of times, because there's definitely, it's because it's a probabilistic tool. It's just how we actually work within that, looking at these probabilities of failure. And I really liked some of his sort of coefficient of variance work, and how we kind of how we ultimately how do we use it in a way that just can produce a really robust probability of failure number that's kind of usable and means something, and there's all sorts,
So honestly, like what I just was thinking about, I do 3D like DEM modeling, discrete element modeling, and it's for the lab test. So they're basically the lab tests that we do here in our lab. And I was thinking that maybe I could take my VTK files out of my 3D model and import them into 3D POV, and then come up with the probability of the fragmentation.
So what's the test?
Oh, it's a new test. It's called shorting pixels. And you can just even go with the Brazilian test, or even 3-axis test.
So you've got your files? They are
VTK blocks. Files that you can. No, they're not blocks. They are spheres. So I don't know if you have seen the
spheres, but that's what I mean. They're an enclosed volume.
Yeah, they are enclosed volumes, but then it's for example, if you're modeling a cylinder, it's just like a cylindrical object filled with little spheres that act as the grain. And then we load them, and it breaks, creates fragments and the fracture planes and everything. So it's kind of a small scale of the field, as you can think about it that. But then you can probably get the outputs of this fragmentation, this loading and this fracturing process, and import them in the 3D POV, and get the probability of the failure and the number of the fragments that we create.
Well, the 3D POV though it's specifically designed for. Effectively, it's sort of, if I've got a slope and a block, it's taking this slip surface straight out to the slope. So we know, we know where it wants to fail, and therefore we can just say, okay, we've got certain forces, we're just resolving those and just saying, okay, we've got some rock mass strength and we've got some joint strengths. Your case is a bit different because you're sitting inside a cylinder. The cylinder doesn't go anywhere. You don't need 3D POV, really. I mean, I don't know.
Just for the sensitivity analysis, I thought about that one right now. It's not a major idea of mine. It's just came up to my mind.
Yeah, I wonder.
It's not possible too.
I mean, I like the idea of being able to just do things quicker, and limit equilibrium is it's a fast solution. So it's instead of your discrete element models probably take days or
no 2.5 hours. So it's not that bad.
Oh, okay. Okay, yes, yeah. Yeah, I'm honestly not sure. You should say, well, yeah, tell you what, send me. Well, actually, you got VTK. Yeah, I don't know, honestly. I don't think it would do it. Yeah, we'd have to. Yeah, honestly, you'd be better off taking Cole's paper. There was a reference in the there was a reference on this one of the slides
Yeah, we
at
have
the
it
bottom.
recorded. I'll go and check that out. Yeah.
And you could take that and you could probably actually implement it pretty quickly yourself. I don't think it took a long time, but
okay. Yeah, thank you very much. And I don't see any more questions coming in, so I think we will end the meeting here. And thank you very much for coming.
You're welcome anyway. Thank you so much to everyone, and that's been patient.
Thank you, everyone. Yeah. And bye.